Okay, so we're going to find all triples of rational numbers x, y, and z such that this equation holds. Now, on the surface, you might be able to spot that when x, y, and z are all 0, it indeed does satisfy, but can we find all rational solutions to this equation? Well, that is actually a pretty interesting problem. In fact, I would say that the solution teaches us a very useful technique in solving many similar problems. So let's delve right into it. Firstly, because x, y, and z are all rationals, we can, let them be a ratio of integers. So we're going to let x equals to a over b, where a and b are integers. And also y equals to c over d, where c and d are integers. And z equals to e over f, where e and f are once again all integers. I guess it's also important to state that b, d, f cannot be 0. Okay, so now it seems pretty natural to just plug these let statements into the equation, right? So we would get a to the 5 a to the 5 over b to the 5, and then plus 3c to the 5 over d to the 5, and then plus 9e to the 5 over f to the 5. This will sum to 0. And now we can clear denominators because nobody likes denominators. If you have an equation with only integers, at least you can consider things like divisibility, right? So let's clear the denominators. Multiply both sides by b to the 5, d to the 5, and f to the 5. Okay, so I've removed the denominators, but what do we do next? I mean, this looks like a complete mess of variables. So how can we manage this? Well, there is a very good way to clean this equation up. See this ADF over here? We can let ADF equals to n1. And notice that this will make this part equal to n1 to the 5. And similarly, for this part, we can let CBF equals to n2. And over here, we can let EBD equals to n3. Now, one concern you might have is that, take a look at this, n1 and n2, they are not dependent of each other. If f varies, then f will affect both of these variables. So you might have that concern, but it turns out that's not going to be an issue at all. You will see later down the road. So if we make the substitution, we get a very simple looking equation. We would get n1 to the 5 plus 3n2 to the 5 plus 9n3 to the 5 is equal to 0. Much simpler. Okay, so I've moved our equation over here. Now, notice that we have 3 times something and 9 times something. These two are both a multiple of 3. And when you add it with n1 to the 5, you get 0, which you can think of as a multiple of 3. So therefore, n1 to the 5 is also a multiple of 3. We can therefore conclude that n1 must be divisible by 3. So we can let it be equal to 3n4, where n4 is some integer. And therefore, we can make this substitution into the equation. And I'm going to start by writing over here because if I write down here, I'm going to run out of space for what I want to write later. So if we let this into the equation, we get 3 to the 5 and 4 to the 5, and then plus 3 and 2 to the 5, plus 9 and 3 to the 5. This sums to 0. And right now we can divide both sides by 3, so let's do that just because we can. So we would get, now, notice that we have n2 to the 5 on its own. And once again, these two are both a multiple of 3. So therefore, n2 to the 5 must be a multiple of 3. And therefore, we can conclude that n2 is a multiple of 3, meaning that it's equal to 3 and 5 for some integer n5. And of course, we can let this into the equation once again. So over here, we would get 3 to the 4 and 4 to the 5. And once again, we can divide both sides by 3. So let's do that. I'm not going to write another equation. I'm just going to change the exponents. So over here, we would get 3 to the 3, right? And over here, we would get 3 to the 4. And over here, well, this 3 just goes away. Would you look at that? We have 3 times something, 3 times something. This is just n3 to the 5 itself. Therefore, n3 to the 5 is a multiple of 3. So we will let n3 itself be equal to 3 and 6 for some integer n6. Now, if you plug this into the equation, well, you would get, so now that I've plugged in this result into this equation, I get this equation, right? And notice that here, we can divide more than just one factor of 3. We can actually divide both sides by 3 to the 3, or 27. So this would render us, if we divide both sides by 3 to the 3, we would get that this disappears, this just drops to 1, and this exponent here drops to 2. And notice that 3 squared is 9. Oh, I'm so sorry, what was that? So this just becomes 9 and 6 to the 5. Okay, do you see what's going on over here? This equation over here is literally the same as the equation we had at the start. It's only that the variables have changed. Now, what would this mean? Well, this would mean that if you were to repeat this cycle, right, if you just do everything we did over here and repeat that cycle going downwards, you would get the same equation over and over and over again infinitely, right? And as an example, from here, you can deduce that n4 is a multiple of 3. So it's equal to 3n7, where n7 is some integer. And eventually, you'll be able to deduce that n7, so n7 must also be a multiple of 3. So it's equal to 3 times ns1. And you'll be able to deduce, eventually, that ns1 is equal to 3 times something as well, right? So basically, you're able to infinitely descend in this case, such that each of these new variables will always be a multiple of 3. But that would be a contradiction, because notice that each of these new variables that you generate will be factors of n1. And since you're able to go down infinitely, that will make you deduce that n1 has infinite factors of 3. But that's not possible. If n1 is not 0, then you cannot divide n1 infinitely many times by 3 and still get an integer, right? So the only possible value for n1 is 0. Okay, but if n1, so n1 over here, if n1 is 0, then what must we conclude? Well, remember, d and f cannot be 0. So this would mean that a is 0. And similarly, we can see that n2 and n3, they cannot be non-zero because otherwise they would have infinite factors of 3 by similar reasoning. So therefore, these two must also be 0. Now, since b and f cannot be 0, then this would mean that c itself is 0. Sorry, this got erased a little bit. Okay, so c is equal to 0. And since b and d cannot be 0 from here, this would mean that e must be 0. So e is 0. Well, if a, c, e are 0, this would mean that x, y, and z are all 0. So the only triple of x, y, and z satisfying this equation, well, the answer is just 0, 0, 0. And that is the only solution. Anyways, thank you very much for watching this video. If you enjoyed, if you found it interesting, then please do consider dropping a like and subscribing. Thank you very much. Bye.